Hello, and welcome to Tech to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Zach Papiez.
Good morning, and thank you, William. And thank you to everyone tuning into this presentation. This presentation is on cleaning bottom terminated components with a particular focus on cleaning no clean flux. Bottom terminated components, or BTCs, are, by their very nature, hard to clean. They have low standoffs that are typically less than 4 mil off the board. They also can leave plenty of residue behind due to improper outgassing channels. This outgassing problem is particularly prevalent in BTCs, as the residue has less surface area to fully activate. These BTCs are also typically very densely packed on the board, making wash fluid penetration even more difficult. When considering BTCs with a no-clean solder paste, this fluid penetration is of even greater importance. Why clean and no clean? Contrary to the name, it is often very useful to clean a no-clean flux system. No-cleans are very capable of leaving behind active residues due to improper outgassing or broken rosin-oxygen barriers and driving failures. There are many applications where this failure is potentially unacceptable. Under these circumstances, a cleaning process must be adopted in order to drastically improve reliability. Current aqueous cleaning chemistries are designed to use intermolecular forces to soften rosin structures. This is particularly important for no-clean flux systems that come stock with this structure. These chemistries must also be compatible with the cleaner and board materials. They cannot be too reactive as to corrode or greatly wear against these materials. This is accomplished by reducing the reactivity of the material set and increasing the dispersion forces, as well as tuning the surface tension. These dispersive forces, when combined with time and heat, do a good job at softening these rosin oxygen barriers and removing the residue that remains. It is also very important that the chemistry that is selected is proven to have a high affinity for the residues left behind from your process. In addition to selecting a chemistry that is compatible with your process, selecting your cleaning process conditions is an extremely important step. In the current era, the cleaning process conditions are as or even more important than selection of cleaning chemistry. The largest of these conditions is the selection of your cleaner itself. The two major types of board cleaners, batch and inline, are both commonly used in industry today. When cleaning a no-clean flux with dense low standoff components, the inline cleaners do appear to be the better option. They are typically better at getting impingement for and extending the total time that the cleaning chemistry comes in contact with the low standoff flux system. This inline setup also allows the board process to be fully automated, and current iterations of these cleaners are made in a closed system, which is much more eco-friendly. That being said, the batch cleaners still do a great job at cleaning, but may struggle with the most difficult to clean components and board layouts. The conditions inside the cleaner are also of the utmost importance. A good cleaner requires heat energy to aid in its mission. This comes in the form of high temperatures, typically between 50 and 65 degrees Celsius. The mechanical energy from the fluid spray is also vital. The angle of the spray nozzles and pressure applied factor heavily when achieving impingement under the boards, and this goes doubly for the low standoff bottom terminated components. No-clean systems need as much impingement as possible in order to clean. The belt speed must also be factored in, as this heavily affects the amount of time that the impingement can be achieved. Bottom line, you need proper heat, impingement, and time for these cleaners to do their job properly. Adopting a method of evaluating your no-clean bottom terminated components is also very critical. It is important to have multiple types of testing to ensure the initial and continued cleanliness of your process. There are a few methods out there to determine cleanliness of your boards. Many opt for bulk extraction methods combined with a litany of electrical tests, but the clear standouts are IC, ion chromatography, and SIR, or surface insulation resistance. Both these test methods go a long way to test the electrochemical environment present on the board after cleaning. They can also be great aids in developing your cleaning process as you're creating it. Starting with ion chromatography, IC is an invaluable tool for identifying ion species on PCBs and other assemblies. IC is a type of high-performance liquid chromatography that uses ion columns to identify both the species and concentration of different ions that may be present on the board. It is particularly useful in the realm of failure analysis. It can be conducted on commercial circuit boards that have experienced a failure and potentially pinpoint the culprit ion species. For no cleans, it is very useful in identifying and quantifying the weak organic acids often left behind. Next, we have surface insulation resistance. SIR is a holistic electrochemical test. It is conducted by testing the resistance between comb patterns with a specific material set under temperature, humidity, and bias voltage. This creates the necessary conditions for electrochemical failure to occur. Bottom terminated components with plenty of residue left over will provide ample ions to drive this failure. SIR is also an extremely useful tool for qualifying your cleaning process and ensuring that it continues to perform. For example, SIR can be used to correlate an electrochemical profile to your bath life and monitor it as it ages. This could provide insight as to what bath life is acceptable for a given process, which would be invaluable for tuning your cleaning process conditions. We can take a look at a brief SIR case study that shows both the value of properly cleaning no cleans as well as the method for evaluating them. On this slide, you can see the SIR test coupon that was used for this particular example. For our purposes, we are going to focus on the QFN 48-1 in the lower left-hand quadrant of the board. This QFN is a bottom terminated component that is frequently used in SIR testing. On this slide, you can see the log ohm surface insulation resistance charted over time for the QFN 48. There were a total of 9 boards tested at 3 different belt speeds of 0.5, 1.0, and 1.5 feet per minute. They were made with no clean solder paste and then cleaned with an aqueous cleaning chemistry at 15% concentration at 130 degrees Fahrenheit. The 1.5 and 1.0 feet per minute conditions showed as yellow and red respectively, or as red and yellow respectively, showed resistance values that exhibited wildly erratic behavior, which was especially prevalent at the 1.5 foot per minute belt speed. This is a strong indication that there is active residue remaining on the board. The active residue, combined with the temperature and humidity of the test environment, showed signs of ion mobilization and failure. The 0.5 foot per minute condition, conversely, showed high SIR values with an absence of any of the erratic charting the other 2 conditions exhibited. This would be a good indication that the slower belt speed was able to remove the majority of the active residues. The 1.5 foot per minute condition may have also been subject to a partial cleaning problem. When the oxygen barrier of no clean flux systems is broken by a cleaning process, but the active residues aren't removed, failures like this one, the one seen here, can occur. In addition to this, to confirm the presence of residues, the compounds were sheared off and imaged. The QFN parts ran at 1.5 feet per minute. The belt speed showed an ample residue, especially in the left picture. Copious amounts of residue can be seen. The residue seen in these 2 images, if active, would be more than enough to drive failures shown in the SIR chart. The QFNs ran at the 0.5 foot per minute belt speed condition can be seen to be much lower, to be much cleaner. It can be noted that there is still some residue left behind, as this component is particularly hard to clean, but it is far reduced. As compared to the previous slide, the remaining residue has retreated much closer to the center lug and away from the pins on the perimeter of the component. Bottom line, the slower belt speed led to a much cleaner part that tested with much better SIR data. The bottom terminated component combined with the no clean flux required a very rigorous cleaning process. Finally, let's go over some frequently asked questions on this topic. The main question for this subject, and one that was hopefully answered over the course of this presentation, is why are BTCs so hard to clean? In general, is that they have low standoff heights and are often packed densely together with other components, making wash fluid contact more tricky. Another question that is often asked is how the IC data compares to the SIR data. And the answer is that it depends. The golden scenario for these 2 test methods would be that the SIR exhibited a failing data set and the IC could identify the ion species responsible, as well as its concentration on the board. They fundamentally test different things, but can often be used in conjunction to identify and pinpoint failures. Finally, many ask how they can tell if their BTCs are clean enough. Test methods such as SIR and IC can serve as process qualifiers and monitoring tools to ensure that your process is clean and stays clean. This concludes my presentation. I'm going to hand it back to William. Thank you.
Thanks, Zach. Thank you all for watching this Tech to Tech session. If you'd like to discuss this topic further or have any questions not answered in the session, please contact your local Kaizen regional manager or send an email to tech@kaizen.com, and we will have someone follow up with you as soon as possible. Do you want to have exclusive access to future content sent directly to your inbox, or do you know someone who would benefit from these sessions? If the answer is yes, just go to tech2tech.kaizen.com, fill out that subscription form. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.